Hello. We did some of the problems in live section, but I wanted to just send you guys walkthroughs to the rest of them in case you want them. Yeah, so we did the first scheme one, but we skipped this one, decay. So let's start with this and then I'll do the other Python ones next. Okay, so let's read this problem. Suppose Isabel bought some turnips from the stock market. And has stored them in random amounts among an ordered sequence of boxes. Okay. So her friend Tom Nook can time travel and fast forward 1 week into the future and determine exactly how many of Isabel's turnips will rot over the week. So basically how many you have to get rid of. Assuming that all the boxes will rot in order, so box 1's turnips will rot before box 2's turnips, we want to determine which turnips are still going to be fresh. So we're filling in this function decay, and we have some list like 1, 6, 3, 4, and then these represent like Isabel's like different boxes, right? And then if we say that 5 turnips decay, then that means this 1 decays, and then 4 other ones decay. So namely this 6 becomes a 2. So you basically go in order and keep subtracting until you have no more turnips left to decay. And the test case I did over here was this one. Feel free to pause and try the other ones. And then I recommend you pause and actually try the problem as well. But I will go through it in 3, 2, 1. Okay. Yeah, I don't know why I did the countdown. But anyway, the way we're going to approach this is, since there's probably a bunch of conditions, I think we should just use a const statement like we used in this problem here. And let's try to figure out what our conditions would be. So maybe the first condition could be a base case. Maybe no turnips rot. In the case that rotten is 0, so if rotten is 0, what do we want to do? We don't want to do anything, right? We just want to return the original list. So there's no decaying to do. We just return our list. Okay, so that would be like our first condition. Now, there's 2 more conditions to come up with, and I'm going to use examples to illustrate those. So let's say I had 4, 6, 2, 1, and then I was decaying 3, right? We know the answer to this, we just removed 3 from the first one. So the reason I'm splitting this up is because the only box we have to change is box 1. And the reason that is because this 3 is less than or equal to the amount in the box 4. So our other condition can be if rotten is less than or equal to, I guess less than works. I don't know how you do less than or equal to in scheme. Rotten is less than car of list. Then what we want to do is just return the same list, except we want to change the first element. So the first element actually becomes the first element car list minus the amount that rotted away. And I know I'm not writing this in like a mix of Python and scheme. I'm not sure why I'm doing that. But this is some sort of pseudocode to guide like how we write it. And then this has to be like the first element of our list. And then the rest of our list is just going to be, well, the rest of the list. So then the rest of our list will just be the cutter of the original list. And then the last case we have is when rotten is actually not less than car of list. In that case, so let's say in this case I decayed like 5. Then I want to take away all of the ones from the original box. So I want to make that 0. And then I want to take away however many I have left to decay from the next box. So in this case, that'll just be taking away 1 from 6, and this will be my output. So let's put this into scheme code, because I don't want to write another fake pseudocode thing. So the first condition we said was is rotten 0. In this case, we just return list. And then I need another set of parentheses around these, because in con, you basically have a list of different like condition expression pairs. So this is the first pair. Okay, so let's make another pair. And the condition is rotten less than car of the list? So is rotten, you can imagine the less than sign is just in the middle, less than car of list. If it is, then I want to create a new list perhaps, whose first element is car list minus rotten, and whose second element is just the rest of the list. All right, let's try to erase our pseudocode here to get rid of some of the confusion. Okay, so we have our two cases here. The last case is if this is not actually true. So that would just be like our else statement, right? So else, what do we want to return? Well, what do we do in this example when we decayed more than 4 boxes? So let's say I was decaying 7 in this like first list. Well, in that case, I get rid of all of these. So the first element of the list that I return is just 0. The second element is decaying 2 from the rest of this. Why am I decaying 2? Oh, sorry, 3 from the rest of this. Why am I decaying 3? It's because I've already decayed 4 of them. And 7 minus 4 is the number that I have to decay. So I'm calling cons of 0, and then I make a recursive call to decay the rest of the list by what I need to still decay by, which is my rotten minus the car of my list. All right, and that's the else. Let's just check the solutions once. Haven't looked at them. Okay. So they had a case for if boxes is null, which I didn't actually check. Yeah. And then they checked if rotten is less than the first element of the list. In that case, they did the same thing as us. They just subtracted out the rotten elements and then returned the rest of boxes. So they created a new list. Okay. And then otherwise, they created a new list with 0 and then decaying the rest of the list, but subtracting car of our list from rotten. Okay, so that's fine. What that means is basically that my base case was sort of unnecessary. Because what would end up happening was my base case would just fall under this case, because 0 would just be less than car of boxes. Okay. Yeah, so we'll change that a little bit, and I also used lists instead of boxes, so if that's confusing, my bad. So this should be like boxes, everywhere where I said list. Okay. Yeah, let's do some Python questions. So we did collapse already. Let's do combine to 61. So combine to 61 takes a list of positive integers and returns true if a contiguous sublist combines to 61. And you can combine elements by either summing or multiplying. So let's look at an example of like something that works. Here we have 6, 10, and 1. And I can do 6 times 10 plus 1 equals 61. And that works, right? That gets me 61. So any combination of addition and multiplication, the only guarantee is that, the only requirement is that the list has to be contiguous. All right, so let's look at the template they made this. The template we have is that we have with sum and with mul. And this is sort of like giving us the hint of like, we split our thing up into 2 cases and then we somehow combine them. And they actually combined them for us, saying with sum, return with sum or with mul. And what this means is that, okay, either attempt to combine the next element with a sum, or attempt to combine it with a multiplication. And if either of those work out and you get like a valid 61, then you're done, and then you return true. So, hinting to that, we want to return true when num so far is 61. So that means we basically reached 61. This num so far is just keeping track of like what number we've created so far. Okay, and when do you want to return false? Well, I think there's a couple different ways you can approach this. The way I think makes most sense to me is if num so far exceeds 61, because I believe this is just a combination of positive integers. But I think the answer key did it a little differently, and we can look at that as well later. Okay, so we don't know what goes on the left of these ands here yet, but we can try to figure out like what the helper calls are, because we said that with sum means include the first element. So if I had like 2 comma 6, or sorry, sum the first two. Sorry, 2 comma 6 comma 10. Then I want to do 2 plus 6, and then whatever else. Okay, so what that means is I call a helper on some list, and the list that I call it on is not including the first element anymore because I've already done some operation with the first element. So I call helper on just 6 and 10, which is just list of slice 1. And now the question really is, what is my num so far? So imagine this. Imagine I called this function helper with this list 2, 6, 10, and said, okay, I've already accumulated, say, 30, right? What can you get me? Can you get me to 61? So what the with sum is doing is saying, take this 30 that you've already accumulated however you wanted, then add the first element to it. So add the 2, and then somehow make a combination with the rest of the list that gets the remaining elements. So this would be 32. So this just means that I change what my num so far is, because now I've done 32 so far instead of 30. So I can just call helper on the slice list, and num so far plus 2. Now, alternatively, if I had, say, the same thing, but I was doing the with mul case, well, that means that I want to multiply what I have so far with 2. So that just means I do 30 times 2, and that becomes my num so far. So again, I call it on list of 1, and then I do num so far times the first element of the list. So now I kind of see what the ands are for. Hopefully you see it as well. There's a problem here in that you can't access this list of 0 unless it exists. And what if I just had like an empty list remaining? Well, that wouldn't work out, right? I'd get an index out of bounds. So I just have to check if list is not empty. Well, one way to do that is just do list, because it would evaluate to a true value if it's non-empty. But you could also do something like, is len of list greater than 0? Okay, and now we finally want to figure out what we want to return. And that just means when we're returning, we have this helper function. Right, we want to make a call to this helper function, otherwise we wrote it for no reason. And we'll call it with list and what we've accumulated so far. Well, what have we accumulated if we haven't done anything yet? That would just be a 0. So there's a slight caveat to this problem, which I actually didn't talk about, which was that okay, this solution works when I choose to kind of multiply, like, let's do another list, 2, 6, 1, 5, or 2, 6, let's just do the 2, 6, 10, 1 example, right? The solution works when I kind of want to include all of the elements in the list, right? Because in both of these, we're including all of the elements. Or all of the elements, or like until I get to 61. But what if I don't want to include, say, like this 2 at the front? And in this case, I actually want 6 times 10 plus 1, right? It's not so obvious why this case would actually work from our solution. And that actually has to do with this choice of 0 that I briefly mentioned as our starting. So let's just walk through it. What I would do is I would pass in this 2, 6, 10, 1 with 0. The with sum case would say, okay, take 2, add it to 0, so we'd get 0 plus 2. Let's make a little tree here. So we'd get 0 plus 2, which is just 2, and then we'd call it on the rest of the list, 6, 10, 1. But now that we have this 2 to start with, we can't make 61, so that's not good. Well, this multiplication case says, okay, take 2 and multiply it with what we have so far. So that's doing 2 times 0. And that's actually implicitly a way of just not including the 2 at all. Which is why this solution works. Because now we're just calling num so far with 0 and the rest of the list, right? And that's like what if I just called num so far on the rest of the list originally. So it's just excluding like as many elements as I need to, and then once it reaches the 61, it stops, so it can exclude elements at the end as well. So yeah, I hope that made sense. I know there was a bit of nuance there. But yeah, let's do the next question. Okay, so there's 2 more questions. The first one is a make change. So this is similar to like any like count partitions or anything like that, except in this case, we're returning the minimum number of coins needed to make change for n using 1 cent, 3 cent, and 4 cent coins. So this is a little different in that you're counting the number of ways, or like the number of coins as opposed to the number of ways, because count partitions just counts like the number of ways you can partition something, right? So that's the difference here. And what we'll do is just maybe a few different cases. So let's do some of the easy ones. Let's say I have $0 to make. How many coins do I need to use? Well, I don't need to use any coins, right? So that's just 0. Okay. What if I had 1? Well, I'll just use my 1 cent coin. Okay. What if I had 2? I'll use 2 1 cent coins. And this means that there's 2 ways to do it. Oh, sorry, there's it takes 2 steps, 2 coins. Okay, if I had 3, I'll just use my coin with 3. And if I had 4, I'll just use my coin with 4. Okay, but what happens if I have, say, 5, right? Well, with 5, it's, let's figure out what the answer would be first. The answer would be use your, in orange I'm going to write what coins, use your 4 coin and your 1 coin, right? And so the answer would be 2. But it's not really so straightforward, like which coins we want to use anymore. Because in these are sort of like our base cases. But when we have 5 coins left, well, you could choose, okay, do I want to include the 4 or the 3, or do I want to go straight to the 1? In the case of the 5, like the biggest coin just works out. So we do want to split this up into 3 different cases. So if we had some n, then we want to say, okay, let's say you used the 4 coin. So that would leave you with n minus 4 coins to fix n minus 4 remaining coins. Or maybe we use 3 coins. Or maybe we use 1 coin. So those are sort of our three cases. And in each of these, we say we've now used one more coin than we originally had. So what do we want to do to combine these is the question. Well, let's look back at the question. We're saying we want to return the minimum number of coins needed to make change for n using these three types of coins. So these are three different pathways that we can take, and we want to choose the one that gives us the least number of coins total, right? So we want to take the minimum of calling the function on each of these. So let's do that. We said our base case was just if n is 0, we return 0. Oh, I did this wrong. We want a 1 here. What do we notice for these two? I'm sorry, I did another one wrong. If we're doing 3 coins, we can just use 1 3-cent coin. So that's just 1. Okay, so for 1 and 2, namely if n is less than 3, we can just return n, because for 1 it's just 1, and for 2 it's just 2. Otherwise, if, and I did the 4 wrong too, I'm sorry, I kept writing the wrong numbers, I guess. I meant to write the number of coins. Otherwise, if n is basically like less than or equal to 4, then we want to return 1. Okay, those are like our base cases. And now all we want to do is return the minimum of make change of n minus 1, make change of n minus 3, and make change of n minus 4. But that's not quite right. That would sort of be implying if I had, say, 5 coins, right? And then I called make change of n minus 4. That would just return like make change of 1, which is 1. But I actually need to use 2 coins here. So I need to count the coin that I actually just used up in one of these 3 choices. So I add 1 here. Yeah, so this problem is actually a little bit more interesting in that you don't need to do this much work, because, for example, if you do this like n minus 3 and n minus 4, then you need to go down all of these branches, and this tree grows super quickly, right? Every tree has 3 subtrees, and so that would be a lot of recursion, and it would become a lot of work really quickly. So I think one shortcut that you can take is if you had, say, a really big n, right? If you had like n equals like 89, well, in that case, you know that you're going to fit like almost as many 4-cent coins as you can, right? So in this case, you'd fit like 22 4-cent coins in here. So what you can do is you can kind of just like say 89 divided by 4 coins that you're going to use, plus make change of 89 mod 4, which is just 1. And you see this even in like the simplest of cases, right? In the case of 5, we really don't need to split it up into this like n minus 1 and n minus 3 case, because we know we can just use 4 coins, and then we have just make change of 1, which is one of our base cases. So since you can reduce each of these down, this problem can be solved a lot faster. But yeah, it's interesting to think about, because there's some like coin problems, like depending on your choice of coins, where like when you can simplify actually is not like as soon as you exceed your largest coin. So it doesn't always make sense to just keep using the largest coin until you like don't have to anymore. Maybe I can come up with a simple example. You can skip this part if you are bored. Let's say you had like wanted to make a 7 from 6 cent and 2 cent. Let's see. Not 2, sorry. Let's say you wanted to make 7 from 5 cent um, 5 cent and 2 cent coins, and let's make this 7 and 8. Okay, sorry. So in this case, it doesn't actually make any sense to use this like 5 cent denomination, because after we use the 5 cent, then we have a 3 remaining, right? And if we have a 3, we actually can't make a 3. But we could use 4 2s. So yeah, try to figure out like what the pattern is and when you can use things. Oftentimes it's just like if you have a 1 coin, then you can really make anything, right? But you don't always have a 1 coin. Yeah, let's do the next one. Okay, so this is the last problem, which is asking us to create a generator that yields the labels of t in order. And you guys might not be familiar with what is called an in-order traversal of a tree. But let me just draw a tree here, and I'll give you an example. So let's say I have 5. Let's say this is a 3, 9, 1, 4. Okay, so an in-order traversal means that you first yield the left child of a tree, then you yield the root, and then you yield the right child. Not only that, since you're trying to yield values, what you do is you call in order on the left child, then yield the root, then call in order on the right child. So what that would mean is that if I'm, say, at this root node, I'll call in order on my left child, who will call in order on his left child. And this is just a base case because I don't have any children, so that would be the first element. That's a 1. Then you return the root, so that's the 3, and then you yield the right. That's the 4. And remember, this was just this like small subtree that was left of a bigger one. So we've done the left subtree of this 5 right here. So then we do the root, which is the 5. And then we do its right subtree, which is the 9. Yeah, so that's the gist of an in-order traversal. You might notice that these values came out in order. And that was because I drew a special kind of tree called a binary search tree. But yeah, you don't need to worry about that until maybe next semester. Cool. So let's try to do it. The first thing is an if statement. So our if statement looks like a base case to me. And what were the base cases here? Well, the cases that I almost immediately knew the answers to were this 1, this 4, and this 9. And the reason why is because they don't have any children, right? I can just yield that value. So I can say if t dot isLeaf, then just yield t dot label. Okay. And now this is a bit confusing, but we're going to try to do the solution with the template, and then maybe I'll talk about an alternate one. So they're creating some sort of list, and then iterating through presumably that same list, and then yielding the values in it. So the list that's being created here could be like so. So the recursion here is that we want the in order of the left subtree, then we want our node, and then we want the in order of the right subtree, right? So maybe my list can just be a list with in order on t dot t's left child, and the way I get the left child is just get the first branch, 2e dot branches of 0. So I call it in order on the left. Then I want to combine that. Let's see what this list would get me actually. So this list would get me my 1, 3, 4. Then I want to combine that with my 5, which is the root node. So t.label plus the list of calling the in order on the right branch. So t.branches of 1. And that would just mean this 9. So basically I'll do 4x in this list, which is going to be 1, 3, 4, 5, 9. I just want to yield x. And I can change this 1, 3, 4, 5, 9 to the actual list. So another way that you could do this is, instead of doing all this complicated stuff, making a list and stuff, in the else case you could just say, first yield from in order of the left branch, then yield the label, and then yield from in order on the right branch. And in my opinion, this reads a lot cleaner. I don't see the need to create an extra list. Actually, one of my friends pointed this out to me. I'm using his solution. But this is the way you typically do in order traversal of trees. Like, it looks more like this. So I thought it would be nice to show that also. The last thing that I'm going to show you is their solution, which is pretty much the same thing, the CSM solution. Where is it? Yeah. So basically, they created a bigger list with in order of t dot branches of 0, in order of t dot branches of 1, and then they yielded from that list. So that would mean that they created a list like 1, 3, 4, comma, 5, comma, 9. And then they yielded from that list, each of the elements in that list. I guess one very last thing before I leave. They didn't actually create these lists. This is a generator object, because in order just returns the generator object. I actually called the list constructor to get the list from the generator object. Yeah, so that's the worksheet. Just email me if you have any questions. Yeah, see you next week.